So we were talking about numbering systems that are used by computers. So our digital devices. Of course, the computer is a digital device, and no matter what book you read or about computers, they'll get into these numbering systems. I mean, there's a lot of things that you'll understand. We probably won't get into it this semester, but if you take, not this mini term, if you take the ILT 196, which is the advanced PLCs, we'll understand or we'll see where these number systems actually come into play when we set up what we call mask, when we set up compares, and we do other things on this high level these languages, these high level instructions that we have besides just inputs and outputs, which we'll be dealing with this semester. It will come a little bit into play when we start dealing with timers and counters, when we start talking about why do we have these ranges of negative numbers and positive numbers, and we'll figure that out too. So anything we went to buy a decimal. We started off with decimal, then we went to binary. We looked at converting from binary, from decimal to binary, using successive subtraction, and then we learned how to go from binary to decimal using addition. Then we looked at octal, I think, or I can't remember. It doesn't make any difference. Octal, which is a base 8 numbering system. A binary is a base 2. Octal is a base 8, so it means they have 8 characters, 0 through 7. We looked how to go from binary to octal and octal to binary. We did not look at how to go from decimal to octal. Very seldom are you going to do that. What you'll probably do, and what I do most of the time, except for using a calculator, is I go from decimal to binary, and then I set it up in groups of threes and convert to octal. I do the same thing when I go from decimal to hexadecimal. I'll take the decimal number. I'm sorry, go from decimal to hexadecimal. I'll take the decimal number and I convert it to binary using successive subtraction, and then I set it up in groups of 4 bits, starting at the least significant bit, and then I write down what each one of those. But remember, on hexadecimal, we have 15 combinations. And so they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F are the 16 combinations. So we actually start using letters of the alphabet. Like I told y'all, when I was in college, we were assigned to do a base 36. So we used the numbers 0 through 9, and then we used the rest of the alphabet all the way through Z, and that gave us a base 36. And then, so that was a real interesting project. So anybody need to go back over those base conversions? Like I said, in this semester, in this mini term, we're going to be using decimal. But when we get into counters and we get into timers, when we talk about the range that we can count to, and the range, how many negative counts can we have and how many positive counts we can have, then we'll come back and touch on this, and we'll talk a little bit about something called two's complement, which we haven't got into. Anything? And y'all, I can't see when you raise your hand when I share my full screen. Like I say, if I integrate the PowerPoints into Blackboard Collaborate, it's very, very small and we can't see them real well. So I like to just share my whole screen. Any of those we need to go back over? So decimal to binary, binary to decimal, binary to octal, then octal to binary, and then binary to hexadecimal, and then hexadecimal back to binary. So everybody's okay. Speak up or forever hold your peace, right? Okay. So when you take digital, if you take digital, you're going to run into to exactly the same thing. Uh, digital is definitely deals with, if you're in an ILT program, digital is one of your core classes. So if you're an ILT, you're going to take digital. So if you go into that class later in your degree, then you'll find out you probably know about this already, most of this stuff. So this is a just a chart of just counting in hexadecimal all the way up to FF, which would be 255. And this might be kind of small for y'all. So this is in decimal. I'm using two digits because I'm using two digits in hex. So we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we go A, B, C, D, E, F. Then 1, 0. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1 A, 1 B. And the big problem, guys, is when people get to 1, 9, they want to go 2, 0. But that's just ingrained into our blood. So 1, 9, 1 A, 1 B, 1 C, 1 D, 1 E, 1 F. Then 4, 0. So we've counted to 16 4 times. Notice I'm not saying 40, I'm saying 40 because 40 is a term that we use for decimal. Now, if you dealt with decimal, if you dealt with hex a lot, you'll hear people talk about it, and they will call that 40, but they know what they're doing, so they know that 40 is not base 10, but it's a base 16 40. And this takes us all the way up to FF, which is 255. Now, this is going to become pretty important later on. We can calculate the number of combinations in any base by taking the base and raising it to the number of digits. So the number of combinations, the little formula is, and that's including 0 now, is the base raised to the number of digits. Of course, the digits in base 2, we call them bits. So how many combinations can we represent with 2 digits of base 10? Well, it'll be 10 raised to the second, and that gives me 100 combinations, which would be 0 through 99. So how many combinations can we represent with 8 bits of binary? That'd be 2 to the 8th, which is 256. Now, that's including 0. The biggest number we can do, so the biggest number you can do is the base raised to the number of digits minus 1. So 2 to the 10th gives us 100 combinations, including 0, and then minus 1 would give us the biggest number we can represent would be 99. So the biggest thing I can represent with base 16 would be 16, right? On this one would be squared, which would be 256, because we're using 2 digits. So if I've got 4 hex digits, that's going to be 16 raised to the 4th, which is 65,536 base 10. Or the biggest thing we can represent is 65,535, but that would be 4 hex digits, and that would be F, 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 F. If you converted that over to binary, it's going to be a string of 1s. If you add them all together, you come up and get 250. So 16 bits of binary. If you ran off the chart, that's 2 to the 16th, which is 65,536, which is the exact same thing as 4 digits of hexadecimal. But 16 bits of binary would be extremely long, where I can use 4 digits of hexadecimal to represent the same thing. So what we use hexadecimal for in octal is to represent large binary numbers. So we usually don't go from base 10 to octal. In fact, if I was going to go from base 10 to octal, I would probably use a calculator that had bases on it. By the way, I know the default calculator for iPhones don't have programmers option, but there is a calculator you can download. I forgot what it's called, which would have basically the same options that the Windows calculator has, which is a really good calculator. So this would be counting in octal. This is basically the same chart. Here I'm using 3 digits: 0, 1, 2, 3, 4, 5, 6, 7. Right. So this is octal on this side. I should do that. So I don't know what this is. Octal counting examples. 1, 2, 3, 4, 5, 6, 7. This is octal on this side. I don't know what's going on over here, guys. I have no idea. So I need to go back and look at that. Codes. So if all a computer can deal with is ones and zeros, we've got to be able to represent something more than just numbers. So when I come up here and look at my computer keyboard, if this was nothing but binary, then I wouldn't have all these keys right here. By the way, this is called a QWERTY keyboard because it's got that name because this list of characters. So when I come up, this computer has no idea what the letter Q is. Everything's got to be represented with a code. So we have it. We'll look this up. This is a compatible computer, so it uses a key scan. We call them a key scan code. So when I come up here to hit this Q, there's a code of ones and zeros that represents the letter Q. So a code is when we use one thing to represent something else. And so y'all been using codes for a long time, but you've been doing it by just hitting these keys. Right, you understand? So, when I send all this information over the internet, we're sending tons of codes. And we'll look at these things you call emojis too. So that's codes also. Go ahead. Not for you, for the inside of the computer, for the processor. No, they are codes. It's not the number one. It's not it's a what we call a key scan code. So just to give you an example, I'll come up here and I'll go here and then I'll go to I should have brought it up. I thought I had it in here, but I'll look at oops. Oh, I got it up here. So we'll just do we'll just say key scan code. So these are the key scan codes, if it pops up. Key scan codes. So when you hit the number 1, it is a code. It's not the number 1. It's not even the binary number 1. It is a key scan code. That's not what I wanted. Let's put oh, I don't know what it's spelled, but I'll find it. So I don't know if that's not the key. Let's see. We'll see if I can get a better image. Yeah. So here's the actual codes, and they're give you in hexadecimal. If it does, it's going to take me to a site, guys. So here's the key scan code. So when I hit the number 1, it sends a 1B. Now that's hex. It's giving it X. I'm sorry, 16. So it sends out 0001, 0110 is the code that it sends. So this is the actual binary codes. Of course, they've given us to it in hex because it's a lot easier. And also you have a shifted code too on your numbers. So, and this is, and if you've got a auxiliary keypad, just a calculator keypad, the codes are different for the one over here. So the one over here is 69 hex. The one up here is 16. So the codes are actually different between your numeric keys across the top. So when I hit the letter A, it sends 1C, or 00011100 is the code it sends into the application that's running the program at a time. And what's nice is that code can mean anything. So I could be running a flight simulator, and F might be, when it sends the code for an F, that might mean lower the flaps to that application, because all it's seeing is a code. And it's up to the application that's running your program what those codes mean. So this is why we call this a soft keypad. So F is not an F, it's just a code to be, or not to be, right? 0010 1011. That's what comes into the application. Now, if I'm running Microsoft Office or Word, it's going to print an F when it gets that code. If I'm running a flight simulator, it might lower the flaps because it's nothing but a code, and it's up to the application. If y'all have played some games on these computers, and it's actually starting to get very, very popular again too, these high-speed, beefed-up desktop computers, as far as the gaming community goes, they hit the keys, and the keys mean different things to the application, because it's not the letter A, it's 00011100. It comes into the application, and that might mean, display the air pressure. So that's what's neat about these soft keyboards, which is pretty neat. And this doesn't show it, but there's a different code for shift. So if you hit shift, then there's a different code that the A key sends. It might say shifted or unshifted. So everything is in ones and zeros. So a code is when we use one thing to represent something else. But in computers, everything's got to be in ones and zeros. So no matter what you're doing, whatever you input into that computer has eventually got to be in ones and zeros. So this is why we have all these codes. So a code is when we use something to represent something else. It's like your contact list. So that code, that name represents a number. So when you hit that name, your phone knows that name is coded to that phone number. So that's basically what codes are. It's when we use something to represent something else. And everything inside that computer has got to be ones and zeros, everything. There's no such thing as the letter A. There's no such thing as the number 1. There's no such thing. So that's what we have to do. So we got all these codes that we use, which it's been transparent to you. So the first code we'll look at is one that's been around for, good gracious, BCD. This is not a numbering system. This is a code. It's actually in its name. This is a method that we can use. So we're going to look at BCD. We'll look at something called gray code. We'll look at ASCII, which has been around for years. We'll look at real EBCDIC. The book's got that wrong. We'll look at Unicode, and we'll also look at what we call enhanced ASCII, which has been around for years, and it's still used in PLCs. If I want to send information or characters to some type of display, then normally we put that string of characters in ASCII code. But there's also Unicode, which will also look here. I think even the 1100 supports what we call a web server. So what we have to do is we have to understand a little bit about Unicode, which is used by the internet and used by most Microsoft products. So binary coded decimal. Each 4 bits of binary are grouped to form a decimal number. 4-bit grouping represents 10, 11, 12, 13, 14, 15 are not valid. So what we're doing is we're taking the 4 bits. So using 4 bits of binary, that'd be 2 to the 4th, I could represent 16 combinations. The only combination that's legal in BCD is this, and you always use 4 bits. It is a code. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's it. That's all we have. So I'm losing 1 0 1 0. I'm losing 1 0 1 1 1 0 1 1 0 0. I'm losing all these codes. But what we're going to do is when we come up here with BCD, going between BCD, which is not a numbering system, it is a code. We just write a 4-bit pattern that represents the decimal, the 10 decimal digits. So what that means is, if I was counting in BCD, so let me discard this and just add another slide. Oops, I didn't want to do that, Rich. Now the problem is somebody is going to go between decimal and binary using this. Somebody in this class is going to do that on a test, and they're going to miss it. Binary is a weighted numbering system. Decimal is a weighted numbering system. Octal is a weighted numbering system. Hexadecimal is a weighted numbering system. BCD is a code. It's when we use something that is not weighted or something to represent something else. So if I was going to write the number 363 base 10, if I was going to convert that to binary, I would start out by writing a chart. 1, 2, 3. I'm sorry. I got to do this right. 1, 2, 3, Rich. I'm thinking decimal. So we would start out by writing this chart that we looked at before. We'd go 1, 2, 4, 8, 16, 32, 64, 160, 256, 512, 1,000. Well, 512 is plenty. And then I would say 1, 2, 4, 8, 16, 32, 64, 128. Nobody caught me on that. 128, 256. So I would come down here and I would pick out the largest power of 2. I could subtract from that 363, and I would subtract 128. And I would put a 1, and then I would continue down the line until I got to 0. If I'm using BCD, this would be base 10. I would come down and write down this. I would write down that, and I put a space in there, and I would write down this. 3, this is the code for a 3. This is a code for a 6. This is the code for a 3. That is not 1, 2, 4, 8, 16. It's 1. Some people call it the 1, 2, 4, 8 code. So this don't hold away a 16. It goes back and picks up this code, this again. And you always use 4 digits. So if I was going to say 1,973, then I would say 1. So I wouldn't drop them zeros because that's part of the code. 9, 7, 3. This is not weighted. This is a code. It does not go 1, 2, 4, 8, 16, 32, 64. It goes 1, 2, 4, 3. It goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. Some people call it the 1, 2, 4, 8 code. What we do is we directly represent the decimal numbers with using 4 bits of binary. But we throw away 6 combinations. We throw away this combination right here. It's gone. This is not legal in BCD. We throw away this combination right here. It's not legal in BCD. We throw away this combination right here. It's not legal in BCD. We throw away this combination right here. It's not legal in BCD. We throw away this combination right there. That's not legal in BCD. And we throw away that combination right there. It's not legal in BCD. The biggest combination you have in binary coded decimal is this right here that represents a 9. It is not a numbering system. It is a code. We use 4 bits of binary to directly represent each decimal digit. So if I was to see the BCD code, sorry. So if I was to see the BCD code, I don't want to do that. Then this would be 99691. And this would be binary. This would be BCD. It's not a weighted number system. It is a code that we use to directly represent decimal numbers. BCD has been around so long. We have BCD counters. If you take digital, we have counters that count in BCD. We have instructions inside computers that does BCD math. It's a little complicated. It's got to be go through a little algorithm to actually do it. But we do it because BCD's been around so long. But it is not a numbering system. It is a code. But somebody in this class is, I'm gonna say, convert the following digital binary numbers to digital, and you're gonna use BCD, and of course you're gonna miss it. But this is binary coded decimal. It's even in its name, guys. Binary coded decimal. So when you use a code, it's when you use one thing to represent something else. So BCD, like I said, has been around for years. Any questions on BCD? I wish I could say this class has got 7 people in it, and I guarantee somebody will do it on a test. Or on the worksheet that we'll give out when y'all get back. It should be in the handout section if you wanted to go ahead and look at it. And this will be very similar to what we'll do on our first test, where I'll give you a bunch of numbers inside of metrics, and then you convert it to the other bases that it doesn't give it. And I'll show y'all that, but you can go ahead and start looking at that if you want to. Any questions? We okay? It's not a numbering system. It's a code. The processor in the computer's PLC only understands numbers and codes represented with 1s and 0s. All images displayed by a computer are a series of dots that are either on or off. And like I said, when y'all come in next week, we'll get out the magnifying glass and we'll show y'all, and you can actually see these triads in there, these red, green, blue triads on a black background. Computer programs can process binary codes into a series of dots a computer uses to display images on the screen. This means a computer can display binary numbers, and they can do it in binary, they can do it in hexadecimal, they can do it in decimal. It's up to the application how they want to display these dots on the screen. And I think I told y'all, I showed y'all system information last class, where they actually showed the addresses inside the computer, and they use hexadecimal because it was a real large binary number. Guys, I'm going to pause. I got a phone call from my son. So numbers, of course, number systems used by the PLC, they use decimal, which is what we're going to use this semester. So this semester we will be decimal. And then next semester we'll get more in the if you take ILT 196, we'll move over to the Compact Logic PLCs, and there will be a certification, an Allen Bradley certification available in that class. But we'll deal with Sequencers will deal with compares, will deal with math and logic, and I can't remember what else is in the class. Of course, the biggest advantage of binary, I think we've gone backwards. No, well, used by computers to represent, so we know that the computer understands binary, but we have a big problem with that, especially large binary numbers. So the computer is going to display large binary numbers in a different base. Of course, by default, your PLC is going to use base 10, which gets very confusing if you're dealing with binary. But you have to tell it what base. If you don't want to use decimal, then you're going to have to well, your application, your PLC, the PLC itself has no idea what decimal is. Your PLC is ones and zeros. It's the application that's running your computer. When we start looking at the program and monitoring the program, it's by default the application will display our numbers in decimal. But like I said later on, if you take the second PLC class, we'll get into these other high-level commands that's the advantage of a PLC over what we call relay logic. So it's easy to electronically transmit and receive accurately, easy to electronically store for later use, easy to electronically perform math and logic. Disadvantage, of course, it requires a large number of digits to represent decimal numbers or codes. Octal used by computers to represent large binary numbers. PLC Octal is still available on every PLC I've ever programmed. It's not available on your computers anymore, or even your tablets. If you look at large information, if you really get into maintaining your computer, there's a configuration file that the computer automatically loads in. It's called the registry, which has all this information, and a lot of the information in there is going to be either binary or it's going to be hexadecimal. And then, of course, if you look at the system information about the addresses of the PLC itself, or not the PLC, your laptop that's running a Windows operating system, not an Android operating system. Guys, I have no idea how to access the information on an Android computer that's running the Android operating system. But I guess you could find that in Windows. They call it Device Manager, and they also call it System Information, where we can actually see the binary information these guys are actually using. So, of course, hexadecimal, we use hexadecimal to represent very large binary numbers. When we get into, if you take the second semester, when we get into masking, in fact, we do a mask. Masking means you cover up some bits that you're not interested in anymore. Then what we can do is we can come up with a mask. When we come up with a mask, it's going to be binary. And then when you enter it in the computer, you can enter it in as decimal, but it'd be a lot easier if you enter it into hex. So we're probably going to do that a little bit. I think it's when we start dealing with, we're going to deal with a really neat instruction called the move instruction that we can do. Of course, the biggest disadvantage of hexadecimal, it's hard for us to understand. It's hard for humans to understand. Unless you've dealt with it. Of course, you tell, for me, I've dealt with it for a long time. One of the first jobs I got before I went to work for U.S. Steel was working for a computer company on a mini computer put out by Lockheed. So I've been dealing with hexadecimal for a real long time. So it's second nature to me, and I understand it. So it'll take a little while for you to get there. But if you're going to deal with the high level abilities of these program controllers, or even your computer, if you're running a Windows operating system, a lot of stuff that you do within the registry is going to be, you'll enter it in hexadecimal. And so I did go back, so I'm sorry. So undoubtedly. So let's find our codes. So we looked at BCD, binary coded decimal. So what we'll look at now is a code that's been around for eons. This code was originally developed so we could send text to printers, by the way. And it's called the American, so this is an English code. It's called the American Standard Code for Information Interchange, or ASCII. Oh, this is counting in BCD, by the way. And that's a 6, of course. We looked at that formula. Everybody okay there? So the base raised to the n, this gives you the number of combinations available in any base. And then the base to the n minus 1 gives you the largest number that you can represent in that base. Let's see, not a numbering system. Gray code. Basically a gray code. The problem we have, especially when I'm trying to measure the revolutions per minute of a high-speed motor. We've got the fastest we could run a regular AC motor on 60 cycles is 3,600 RPM. That's revolutions per minute. But we get into some of these brushless motors that's available to us now, and some of these motors that's running on computers, hard disks are running at 7,200 RPMs now, and we're trying to count those with a PLC, and we're trying to get real accurate within a fraction. So instead of 100 RPM, we might want 100.5 RPM. As soon as we do that, then that means my counter has got it. My devices have to get me more than one pulse per revolution. So gray code is basically it uses ones and zeros similar to binary, but it's not a weighted number system. It's a code. We can convert it to binary prior to doing arithmetic with it. We used to detect the position of a motor shaft. We also precisely detect the position of a motor shaft. Some of these robots, the encoders that we're getting off those things are down to the nanometers. So that means we've got thousands of these things inside just a centimeter. So this guy, we're going to have to use a code that has the ability to count at real high speeds. I don't know if y'all seen some of these robots actually move. So gray code, this is extremely fast counting code, reduces the propagation delay because only one bit changes between counts. Speed of the operation of the controller system increases because only one, but the problem is we can't do arithmetic with it. So this has to be converted to binary before we can do binary math with it inside our PLC. So this is counting in binary. So over here, this is decimal. So when I go from a 0 to a 1, we have 1 bit change. When I go to 2 to a binary 2, we had 2 bits change. Bit 0 had to go to a 0, and then bit 1 had to go to a 1. When I count to a 3, only 1 bit changed. When I count to a 4, we had 3 bits changed. When I count to a 5, 1 bit changed. When I count to a 6, we had 2 bits changed. So what happens with binary, the number of bits that change between counts varies. So how long it takes to propagate or go through the counter would depend on which count. And we have multiple bits change whether you're counting up or whether you're counting down. So what they did is they came up with a high-speed counting code. It is not weighted. It is a code. And it's called gray code. Now, to convert a binary number over to gray code, and by the way, I took this out. The textbook even has, not the textbook, the lab quiz 3-1 does not do gray code right. But this guy, what we do is we call this an exclusive OR, by the way, and we'll get into logic later on. And the digital symbol for an exclusive OR is it's like this, and then it only always has two inputs. And what the output tells you is if the two inputs we get a 1, which would be a voltage level, out if the two inputs are not equal. So what that means is if I have a 0, by the way, exclusive OR, we put it inside this. We'll find out later on. So in logic, this symbol right here does not represent a plus. In logic, this symbol represents an OR. And if we put it inside a circle, which I can't do, then this represents an exclusive OR. Well, the way the exclusive OR works, if the two inputs are not equal, then we get a 1 out. If they are equal, we get a 0. So if I was going to take a binary number like this, and then I was going to convert it to exclusive OR, then what it says is I'd bring the first bit straight down, and then I would take this bit and I'd exclusive OR it with that one. So that would be their equal. So I would get a 1. Then I'd take a 1 and a 1. They're not equal, I'm sorry. Here I would take a 0 and a 1. They're not equal, right? So we'd get a I'm sorry. So we'd bring this one down, then we exclusive over that with that. They're not equal, I'd get a 1. Then I'd take this and exclusive of that, I'd get a 1. Then I'd take this and exclusive over that, I'd get a 1. I'd take this exclusive with that, I would get a 1. So with that code right there, I would get all 1s, and this right here would be the gray code. But notice, if I was going to go the other way, and we can do this very easy with computers. In fact, a lot of computers will convert this for you, is we would take the gray code and would bring this down, and then we'd exclusive OR that, this with this, then we'd bring this one down, then we'd exclusive OR the answer with this one, and then this is what we'd come up with. So this is the way we would do the gray code. Gray code counters would give you the gray code, so you would have to come up with some method to get it into binary so you could do math with it. Okay. So that's okay. So that's all. We're going to look at gray code. So if I was going to do gray code, I would look it up in a chart. So this is a chart with the gray code. And so, and I thought I changed this. So this would equal to a decimal 1. This would equal to a decimal 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, I haven't paid and skipped any, 28, 29, 30, 31, 32. So when I go count up, so let's say I'm counting up gray code, from a 0 to a 1, I had 1 bit change. From a 0, I'm sorry, I know I did something wrong. I'm not going to put the equal sign out there, guys, because I guess I should have done this. You know, I forgot 0. I started counting with 1, even though I should know better. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. I knew this was an odd number over here. So when we count from a 0 to a 1, we had 1 bit change. When we count from a 1 to a 2, we had 1 bit change. When we count from a 2 to a 3, we had 1 bit change. When I count from a 3 to a 4, we had 1 bit change. When I count from a 4 to a 5, we have 1 bit change. If I count from a 5 to a 4, if I count down, we have a 1 bit change. So we could go on this forever, but it don't go 1, 2, 4, 8, because this 1, 2, 4, 8, that right there would be a 5. But in gray code, it's a 6. So gray code is a code that you cannot interpret directly. If you were good enough, you could take it through that exclusive OR and you can convert it over. But odds are this is going to be done for us, right? You understand? So I'd have a gray code positioner, and then we would bring that into our PLC. And then if we had to do the math, we could do the math. And we might see how to do that if you take the next class. But notice whether you count up or down. So from a 7 to a 6, we only had a 1 bit change. From a 20 to a 21, there was only a 1 bit change. So no matter which way you go, whether you count up or count down, you always have a 1 bit change. So we call how long it takes to cascade through the counters, we call that the propagation delay. So the gray code has a real small, fast propagation delay because a lot of bits are not changing at the same time, which means we can count a lot faster with the gray code. But I dropped that out of the quiz out of the lab 3-1 because this is not a code that you would need to go or convert between. This would be a code that I would go and look it up and go and find a gray code converter because it would just be too hard to come up with all the codes and to come back and do that. But so gray code, high-speed counting code, only 1 bit changes per count, whether you're counting up or down, and that's important to know about this. ASCII code, American alphanumeric codes represent letters, decimal numbers, or special symbols. And then the first one we'll look at is the American Standard Code for Information Interchange, or it's got a it's got an acronym called ASCII. So basically an acronym is when you take a phrase and you take the pertinent letter off each phrase and you use that to create another word. We in computers we have a lot of acronyms that are not true acronyms, but ASCII is a true acronym. Used to represent alphabet characters. And by the way, I didn't upgrade this because this is not any alphabet. This is the Latin alphabet, which is what we use. So undoubtedly I misspelled Latin. Oh, I spelled it right. I just didn't do it as a proper. So ASCII is the American Standard Code for Information Interchange. It gives us the Latin alphabet. It gives us decimal numbers, and it gives us some control codes to do things. It's 7 bits, so that means we have 2 to the 7th combination, which gives us 128 different characters that can be represented. Characters and codes. Data is often sent in bytes of 8. And what we did is we have a transmitter. And when communications first came out, getting information between 2 devices accurately was very sometimes not too good. So what they wanted to do is they wanted to come up with a method where we could check for errors extremely fast. So the first method they used was something called parity, which what they would do is they would send the number. So this is the ASCII code for the number 1. And then what we would do is we would reserve the 8th bit. This is back when computers were 8-bit. We would reserve the 8-bit for what we call a parity bit. Now, what they did is they said, okay, what we'll do is we'll set the transmitter and receiver up the same. So we can set it up for even parity. Well, if we set this up to transmit even parity, if this is the transmitter, then this guy had to be set up to receive even parity. And what they would do, parity has nothing to do with whether the number is the code is an even number or an odd number. So here this would actually be an odd number because this bit right here is set. But parity has nothing to do with that. What it does is the transmitter counts the number of ones, and it will put a 0 or a 1 in the parity bit to make the total number of ones in the 8 bits even. So here I've got 1, 2, so our transmitter would put a 0 in the parity bit. This goes flying across the communication channel. The receiver counts the number of ones. If it comes up even, it says okay, and it receives the data. If it's not okay, then we have what we call handshake, where this guy would tell the transmitter to retransmit. And a lot of times, when we got a lot of noise going on, you can actually see these downloads actually slow down because they're checking for errors. TCP is what they call a connection-oriented transport protocol for information, and it uses error checking capabilities. It doesn't use parity, but it uses something else to check if the information that your computer receives was the same information that you're getting from whatever website you're trying to download information from. So this is parity. So we got two types. We could have odd parity. So odd parity, if I sent this, which is the ASCII code for the number 1, what it would do, that's not the ASCII code for number 1, Rich. See, I'm lying to y'all. Y'all didn't figure that out, though. So this is the ASCII code for the number 1. It's 1000001. But it wouldn't change the parity. If I was set this up for odd parity, then this guy right here have to be odd parity. Then the same number, or the ASCII code for the number 1, then the parity bit would be a 1 and make the total number of ones in the entire 8 bits always odd. And so if this went over and then a bit changed, then my receiver would know that what it received was not correct. Parity is around 90% capable, 95% capable of finding an error. But when you transmit, huge amounts of data, especially when you save it on your hard drives or your mass storage device, 95% is not good. So we have other error correcting that's a lot more accurate. We have what we call ECC, which is like 99.99999% accurate. But it doesn't deal with bytes. It deals with frames or big a bunch of bits. So y'all can look up ECC. No, it uses CRC. ECC is automatically detects and repairs. So this is the ASCII code chart, and this is in hexadecimal because if I was going to do it in binary, it'd take up a lot more space. ASCII is a binary code. So if I was going to write my name, if I was going to send my name using ASCII, my first name, I would find the ASCII code for an R, which would be a 5. And then, so this said the most significant digits is this way, least significant is this way, and then I would write down a 2. And then a lowercase I, so here's a lowercase I. Then I would write this right here, 9. By the way, I've sent this, I posted this on I think Facebook, and I said only a real nerd could read this. Is what I wrote out. But it was a bunch of binary codes. Uh, then I would use RIC, so here's C, so it'd be another 6, and then it would be a 3. And then an H would be a 68. And this would be the ASCII code for a C. This was used for years when printers first came out. This is the way we send information to printers. Actually, it was developed by teletypes. If y'all remember the old teletypes that we were trying to send information over the phone lines. This was replaced Morse code, by the way. So now instead of me trying to look it up in the chart, your printer would receive this code and it would select an uppercase R and it would print it out for you, which is pretty neat. But we've also got to be able to do things with this. So parity, if I was running even parity, this right here, my parity bit here would be a 0, 1, 2, 3, 4. Here would be a 0, 1, 2, 3, 4. Here would be a 0, and here right here would be a 1. And that would be with the parity bit. Not only do we have to send characters, but we have to tell the, so let's say this comes up to be, this bit right here goes to a 1. Well, when my receiver says 1, 2, 1, 2, 3, 4, 5, I'm running even parity. It says, well, I got a parity error. Well, what does it need to do? Well, what it would do is it would send back this code right here, a not acknowledge. So it'd send back a 1.5 hexadecimal. This would go back to my transmitter, and then my transmitter would resend the data. If it came back right, if this was a 0 and it came back 1, 2, 3, 4, then it would send an acknowledge back to my transmitter, and then my transmitter would transmit the next character. Bell, so this would ring the bell. Backspace, this tells my printer to do a backspace. Form feed, vertical tab, line feeds, horizontal tabs, carriage returns. So what we have the ability to do is control these printers. And most new printers, even though most of them now are graphics printers, they still recognize these ASCII codes. And a lot of times when you look, you see something pop up, and you'll see this, that right there, and it'll pop up, and there'll be some information. That's 20. So 20. That's the ASCII code for a space. So this is the way HTML, hypertext markup languages, tells your computer to do a space. And every once in a while you'll see this pop up on information when you look, and that's the ASCII code for a space. So this is telling us that this is an ASCII code. So if you ever see that %20, that's hexadecimal, by the way, and that's the ASCII code for a space. So we have the ability with the ASCII code to send the Latin alphabet. We also have the ability to represent some symbols, plus, I know minus is here somewhere, and, %, $, hashtag, open quotes, vertical line. We don't have brackets here. We do have parentheses. We have ASCII, we have apostrophes, we have commas. There's the minus right there. Period, backslash. So we can send all these other codes besides letters and numbers. And this is still available. I wish I could do this on my printer. This printer doesn't have a numeric keypad on it. My Lenovo, it's a nice little computer that I can write on the screen. But when y'all get in, y'all remind me, and I'll show y'all how y'all can do these ASCII codes on your keyboard, on your numeric keyboard. You can enter the ASCII code in decimal. So you'd have to take these and convert them over to decimal. But the ASCII code is a binary code. It's a binary code where we can send characters, but we can also send control codes. Well, what happened over time is we moved away from 8-bit processors and we moved up to 16-bit processors. So what they say, okay, I can send 8 characters now, and then I can still use parity. So what they came out with is they came out with what they, and this is the control codes, and this tells you what they do, guys. That's right out of the book. They came up with something called extended ASCII. Extended ASCII added not only all these characters, but it also added some Greek that we could use. Used to when we did stuff, if I wanted to do ohm, I would have to spell out ohm. But what they did with extended ASCII is they gave us this 134, 130. They gave us a code. They gave us a decimal code for the omega sign. Do y'all see it on here somewhere? Here's infinity. And oh, good. Yeah, right there. So I can show y'all how to do that. So I can type in 234. So I know y'all look up symbols. You have to look up symbols. But if you hit the Alt key and on your numeric keyboard hit Alt and type in 234, then Omega will pop up. So we use that all the time. So I use that more than the symbols. Like I said, I can't do it on this card because it's got to be on your numeric keyboard. And that's what I showed y'all. The numbers across the top and the numeric keyboard are two different codes. So hit the Alt key. If you hit the Alt key and type in the decimal equivalent over here, it will automatically insert this into your Word document, also into Office, any of your Microsoft products. I don't know about Excel. Excel's kind of weird on things. This is extended ASCII. This is not EBCDIC. This is extended ASCII. It's an 8-bit code. So 8-bit code gets us all the way from. So the first 7 bits are the same as regular ASCII. So what this got us this got us all the way from 128 all the way up to FF. But remember, your computer considers every number that you enter as a decimal number. So that means if you wanted to enter these directly into like a Word document or something like that, hold the Alt key and then enter the decimal equivalent. And then your computer will look up that pattern in your video memory for the bit pattern for these different characters. MS Word. Oh, here we go. On MS Word or PowerPoint, press and hold the Alt key and then enter the decimal code for the desired character. So, EBCDIC. The book says that this right here is EBCDIC. It is not EBCDIC. EBCDIC is an obsolete code that was originally developed to use on IBM mainframes. IBM wanted to do a lot of things that wasn't available on ASCII, plus they wanted something that they could copyright, so they came up with a code called Extended Binary Coded Decimal Interchange Code, which is the acronym is EBCDIC. So this is the EBCDIC code right here. So this is EBCDIC. This is not what the book says. The book, and this is right off the internet, by the way. I cut and pasted this. I need to give somebody credit for it. This is EBCDIC. So the book says extended ASCII is EBCDIC, but that's not true. So the book is not right on that. This is not a code that we use. Like I said, this is an obsolete code. It was originally used by IBM computers. So on IBM, you had to buy an IBM printer. So one of the jobs I had, guys, was interfacing a standard computer printer that used ASCII codes to an IBM computer. It was a really, really interesting task that we did through the serial ports, and they loved it because they were so much cheaper than an IBM printer. This is Unicode. This doesn't stand for anything. That's not an acronym. Originally, when we did stuff on the internet, everything was done in ASCII, and it was with a formatting language called HTML, Hypertext Markup Language. And sometimes I don't think you can still see the HTML anymore, but used to you could actually display the HTML of a web page, and I don't think that's available to us anymore. but this stood for Hypertext Markup Language, and it was originally in ASCII. So you'd have all these symbols and everything, and basically, so it would tell your computer how to put a web page together. So it wasn't a programming language, it was a formatting language. So we would send a picture and we'd say, okay, we'd put it, have these codes we'd stick in there that we would say, we want to put this in the upper right hand corner. So the picture would actually be sent, but it wants to know where to put it at. So this is called HTML. You can still do it. I got involved with it. I actually wrote Bessemer State Technical College's first web page using HTML because there was no compilers available that we have available now where you can actually pull a web page together and type stuff up and then compile it over to HTML. So it was originally ASCII. So ASCII is still popular even on programmable controllers sending text information. Well, what they realized was a lot of countries does not deal with the Latin alphabet. So what they did is they came up with another code that we refer to as Unicode. There's actually 3 versions of it. There's Unicode 8. It's an 8-bit code, which gives us 256 symbols. Hex 41 through whatever it is, those are the old ASCII codes, but they're using other symbols, which is available. UTF is 16-bit. That gives us 65,536. This is what's used by Office products to store symbols and stuff in there. So I can show you all that right now. So right over here, I'm gonna come over here and I'm gonna say insert. I'm gonna insert, but I'm gonna come over here and insert a symbol. And right down here it says, what code is this? It said is this Unicode. So if I go up here to the Latin alphabet and I look at an uppercase A, uppercase A, this is hex, by the way. It's displaying, instead of 16 bits in that little old tiny block down there, my computer, my application is doing it in hexadecimal. Unicode is a binary code. But it's a lot better a computer displaying it in hexadecimal than it is in binary. First, that would be real big. But if we looked at the ASCII code chart, we would find that the ASCII code for the letter A is column 4, row 1, 41. But this is a 7-bit code. All they did is took the ASCII code and just so basically the Unicode 8 is the ASCII code, but it did away with all these control codes. So it added a bunch of symbols over here, which is pretty neat. I don't know if I've got a copy of the 8-bit ASCII code or not. Literally, I could probably split it in there. Unicode 32, I don't know of any place it's being used. I think they're starting to use it on emojicons to send these characters to it. So these emojicons are already in your computer or they're already in your phone. You have to download them. Y'all probably run updates every once in a while to get more of these things. And your emojicon table gets big. But what they're doing to make it display, they're sending a Unicode that has been established or linked to that picture. So when your computer receives that, so we can look at that. I didn't stick that in here, but we'll go up here and say emoji Unicodes. Oh, I could have used the list. So here they are. So this is the Unicode 1F600. That's the Unicode for that one. And that's the Unicode for that one, and that one, and that one. And of course, they keep adding on our phones. I don't know. My granddaughter, we was playing around while we was going on a trip, and we started sending emojicons, and some of them she sent me popped up with a question mark on it. So my phone received the code, but the code wasn't in my phone. The actual picture was not in my phone. So Unicode, this is what we use for the internet to send all types of information. Emojicons, no longer key scan codes. So Unicode is, like I said, even on here. So here's, I want to insert a symbol. Well, if I don't have the symbol, that represents that code, then you'll get a question mark, by the way. So I want to come over here and I want to insert something. And some of y'all have probably done this before, but you haven't even noticed this. And I said symbol, symbol, and then down here, I can, a symbol, I got to get into the thing. Right down here is the actual Unicode. So this guy right here is 03C0 or 0000001111000000 would actually be the binary code that's sent. But when they display this, they're going to do it, and this is what I was telling you, large binary numbers, odds are they're going to display it in a code that if I needed the binary code, then I could very easily do it. And by the way, you can get all these too by key sequence. I can't remember what it is. Instead of looking it up on your chart, if you got one that you use all the time, just look it up and say, how to key in Unicodes directly, and you can just type it in on your keyboard, and you wouldn't have to go all the way through these charts to find it. So here's beta, here's omega. Beta, I use that a lot. Micro, I use that a lot. But a lot of times on a regular computer, I'll just hit Alt 230 to get that, because I know how to do that. So this is Unicode, guys. 16 bits, used by the internet, used by just about all Microsoft products, used for emojicons when it sends to you. And what's nice about using Unicode is that usually web pages were in English, because the only codes we were using was the ASCII code, and the ASCII code only supports the Latin alphabet. But now we can go to websites that are in Chinese, they're in Mandarin, they're in Spanish, they're in all kind of languages now. In fact, every once in a while, if you click on a link, it'll tell you need to download the codes to support that page. So all the Unicodes out there, all 65,536 Unicodes, are not in your computer, because they're running in the memory of your machine all the time. When I'm running this, because all I do is pull these, right out of the memory of my machine. So every once in a while, you might not have the code, and it'll tell you need to download the character set. So this is not all of them. There's not 65,536 codes in all these tables. In fact, those codes right there are not even in here yet. So I don't know what these codes are here. This F015, it's not downloaded into my computer yet. So this is 8-bit Unicode. So they've dropped, it is 8-bit. So what they've done is they've dropped parity out of here, because it's sent over the internet, and it uses another error checking scheme. So this is 8-bit Unicode. Of course, I couldn't get up to 16-bit Unicode. But notice the ASCII code is still here. So uppercase A. Oh, this is in decimal, guys. No, it's not. It's in hex. 41. If we looked at the 7-bit ASCII code and looked at it in ASCII, in hexadecimal, it would be 41. Lowercase letters start at 61. Numbers start at 31 hex. 30 hex. If we looked at the Unicode 8 or ASCII code, we'd see the same. So what they've done with Unicode 8 is they've just brought the old ASCII code in there. So that way, if you get into an old website that's using ASCII, your computer will still support it, still display it. So I couldn't put 16 up here because that'd be 65,536 cables, and I definitely couldn't do the other one 32 bits because that would be a lot of characters. So that's it for this. That's it, guys. That's it for this codes and numbering systems. Any questions? Okay, guys, y'all take a 10-minute break and then we'll start into chapter 1.